Okay, so in terms of NP hard and NP complete definitions, I just wanted to go over that. So where's that gone? Okay, so in terms of completeness of a language, if we have two languages, L and L prime, we can reduce L to L prime, which is a function which maps one language to another language, where for any string or for any word x, we have, if x is in the language, then some polynomial derivation of that word is in another language. So for all values of, for all x in sigma star, where this is just the set of all possible words, including the empty word, x being in some language L has a two-way implication with f of x being in L prime. So all this means is there exists some function f which maps words from the language to words in this other language, and we'd say we've reduced L to the language L prime. Yeah, and so as Danny says, if we can solve L prime, then we can solve L. Not quite, actually. No, I believe it's if we can solve L, then we can solve L prime. Right, so yeah, if this is decidable, if this is decidable, then that implies that this will also be decidable. So the decidability of L prime implies that L is then decidable. And in the same way, the undecidability, or the contrapositive of this, if L is not decidable, then that means L prime is also not decidable. When a problem of unknown complexity reduces to a problem of known complexity and inherits a known one's complexity. If we reduce a problem to something else, I'm not too sure about that. But if someone wants to confirm, yeah, they can do. Okay, so yeah, we reduce L to L prime, and so yeah, we have this definition here. This is our sort of checking machine definition as well, in a way. We'll go over that as well. But in terms of completeness, so a language is said to be NP hard when every language in NP can reduce to it in polytime. So NP hard is as hard as the hardest languages in NP, and so we can reduce every language in NP to it in polytime. And a language is said to be NP complete when it's both NP, when it's in NP and it's also NP hard. So some languages in NP hard might not necessarily be in NP. To be NP complete, it has to be both in NP and it has to be NP hard as the hardest problems in NP. So, I mean, to prove something's in NP hard, I don't think we'd be asked to do that, to be honest. Right, let's look at the checking machine definition then. NP complete is just saying that a problem where any other problem in NP can reduce to it in polynomial time. Yeah, exactly. So anything in NP can reduce to anything in NP hard in polytime. And so because NP complete is just a subset of NP hard, NP can also reduce to anything in NP complete in polytime. So for a problem to be P or NP, then it must be solvable in... Okay, so for something to be in P, so for something to be in P, that means there's a deterministic Turing machine that decides it. NP, so non-deterministic polytime, is where there's a NDTM, or should I say a polytime NDTM that decides it. So what this means is every possible path is polynomial to the length of the input word. Yeah, and then we have NP hard and NP complete, which we've looked at. So NP hard is as hard as the hardest problems in NP, and NP complete is as hard as the hardest problems in NP, and it's also in NP itself. Not P is just something we can't do in polynomial time with a deterministic Turing machine. No worries. So the idea of the checking machine definition is, I believe there's an example here. Okay, yeah. So apart from the definition using NDTMs, there's another way of defining NP. A language L must belong to NP when there's a polynomial P and a polytime Turing machine M called the checking machine, such that for any word W, this just represents its length, the following two are equivalent. So if the word is in the language, then there's also some other word X, which is polynomial to the length of this word, where M accepts the ordered pair of the word and this X variable. So this is our word, and we say X is a certificate for this word. And so we say X can certify that this word is in the language. So the Sudoku solvability problem meets this definition. So this problem is about, given a partially filled Sudoku board, is there a possible way to complete that Sudoku board? So our word would be a partially completed Sudoku board, and our certificate would be some sort of candidate solution. So let's just say we had a really simplified Sudoku where we can't have things in the same row. Okay, let me 1 2 3 2 1 3. Can't do that. 2 3 1 1 2. Okay, so here we can't have anything in the same row or the same column. And so what we can do is we could say, if we have a partially filled grid like this, is it possible to complete it? It is, because we can put a 3 here, we can put a 2 here. So what our word would be, oops, is it going to change pen? No. Okay, what our word would be is 1 2 3 2 1 3 1, like this, with the gaps. And then our candidate solution, we could say X is equal to what we fill it in with. So 1 2 3 2 3 1 3 1 2. And so this certifies that this Sudoku puzzle is actually solvable. So yeah, this is our certificate, and this is our word, and this is in our language of solvable Sudoku puzzles. So it can't be ambiguous. It can, I mean, we can have multiple certificates that satisfy the same word. Like, there might be another solution in which we could, in this case there's only one way we can really put the numbers in, but there might be possibilities where we can do other things. Yeah, a certificate is the correct solution. A candidate solution is a random one. Right, okay. So we can sort of derive this from our original NDTM machine definition of NP. Suppose that L is the language of some NDTM, that for an input W runs in a time polynomial to W, so it's a polytime NDTM. Then the number of choices is at most polynomial to the length of the word. Given a word W and a suggested list of choices X of this length, we can check in time PW whether this list leads to true being returned. So what this is sort of saying, from my understanding, is it can gather a bunch of different candidate solutions and it can test all of them in polytime, where each sort of root is polytime. That's why it's a polytime NDTM. Suppose that we have polynomial P and checking machine M, then we can form a machine that, given W, guesses a word X of length PW, so we can have all of our choose instructions here. And this checks it in polytime. So this is a polytime NDTM that recognizes L. So here we've gone from our checking machine to our polytime definition. And here we've gone from our polytime to our checking machine definition. So we can go from one to another. They sort of just mean the same thing. One's another way of writing the other though. Cool. Any questions about that? Okay, primitive recursive functions. So the idea of a primitive recursive function, I believe. Okay. So here, any function that can be computed by a primitive Java program is said to be primitive recursive. And so the idea is primitive Java, it limits us to these sort of instructions. We can create variables, increment variables, decrement variables, have conditionals, and have repeat loops, which are count controlled. So essentially like for loops. And we can derive all of these other sort of stuff from those primitive Java rules. And if we can do something in primitive Java, we can say that's a primitive recursive function. If it can be computed in primitive Java programs. So this is the Ackermann function. We have, it takes two inputs and it returns an output. And the idea is this can be computed algorithmically, but we can't compute it in primitive Java. It's not primitive recursive. And so this is significant because it shows us that there's some sort of functions that we can compute algorithmically, but we can't do in primitive Java. Because before this, we thought we could do anything in primitive Java. This creates that sort of function we can't do. Okay, so we pass in two arguments, and it gives us a number output. In some cases, we pass in the two arguments. It calls it with two different arguments. And in this case, it calls it with two different arguments, where the second... Oh, no, okay. Where the second argument calls the Ackermann function again in itself. And so this is a recursive function, but the idea is it always terminates. And to prove that it always terminates, we can use nested induction. So when we want to use nested induction, that means we have some outer inductive hypothesis, and then we have an inner inductive hypothesis. So for any pair of mn in natural numbers, say Q of mn is a statement that A of mn terminates. We can prove that for all of the values of m in natural numbers, and for all the values of n in natural numbers, it terminates. And we can do this by induction. So for our base case, we can say our m is 0, and our n is just n. So for all values of n in natural numbers, this function terminates for when we pass in 0 in, and then any number n. And we can see this because in this first case, if we just pass in 0 and then any number, it will always just return a fixed number. It won't call the function again. So this is almost like a base case. This is our terminating case. Okay. For the inductive step, we suppose that for all n in natural numbers, again, if we pass in some value m and some value n, we want to prove that for all values of n, which we've just stated here, this here terminates. So we want to say, given that this terminates, given that it terminates for some value m, n, we want to show that it terminates for m plus 1, n. And this is our inductive step. So saying q m n implies q m plus 1 n. And the similarity with induction here is this step here. So we have this m here, we have this m plus 1 here. And this is our hereditary step, saying this implies this. And so we do this by induction. The base case, so this is our inner inductive hypothesis. So this is our inner induction. And the base case of our inner induction is q m plus 1, 0. So when n is 0, this holds because m, 1, returns a value p by the outer inductive hypothesis. And so a m plus 1, 0 also just returns p. So we know a m1 returns value p because we proved that with the outer hypothesis, if we pass in anything like this, so m plus 1, 0, this holds because one sec. So I think we're assuming that for the outside, for this outside function, we're assuming that this is true when we're then going into the inner, when we're going into the inner hypothesis. So we can suppose that it terminates for m plus 1, 0, because we've proved that it terminates for 0 something. And so if our m value is the same and our n value is lower than this n, then we're proving that, because that's basically saying q of m plus 1, 0 implies q of m plus 1 n. Our inductive steps here, where n is greater than 0, and by course of values this would be, we can say it holds for some value less than it, so it must hold for this value as well. Okay, a m comma 1 returns a value p by that course of values, and so by this rule here, that means this would also return that value p, because we're just passing m plus 1, 0 in. For the inductive step, we suppose it holds for m plus 1 n, so now instead of just using our base casing, it holds for mn, we're saying it holds for m plus 1 n. And so we want to prove it holds for m plus 1 n plus 1, so we've increased this by 1, and we want to prove that this implies this. A of m plus 1 n returns an answer p by the inner inductive hypothesis, m plus 1 n. So this is our assumption we've got from here. And a mp returns a value q. A mp returns a value q by the outer inductive hypothesis. So the return value of this, the return value of this call here is then passed into this whole function, which then terminates this. So which terminates this here. And so qmn, and so qm plus 1 n plus 1 also returns q. So because this terminates, and because this terminates, and because this terminates, we work backwards and we see exactly what's terminating because of what. Okay, so we're looking at the research paper for 2022. This is question 1, and we've just we're determinizing this NFA. So first, these words are the words that are or aren't acceptable by this NFA. And in terms of determinizing the NFA, we want to look at 0. We want to see what each input from every state, what set of states that can take us to. And I believe this is done. So this is a total DFA. Let me just cross compare. Oh, there is no solutions. Never mind. Okay. If anyone has any issues with this answer, let me know. Why don't you have a separate state for 2 only? Because there's no situation in which we can't be at 2 where we're also at 1. Or there's no situation in which we're at 2 and we can't also be at 1 in that case. Yeah. So whenever we're at 2, there's also a possibility we could take some path and be at 1. And that's why this is in the same state. Does a minimal DFA have a reject state? It does, yeah. So minimal DFA is a total DFA. Is this minimal? A, B, C. I don't think this is minimal. We can merge these two states because they have the same outputs. Yeah, we could minimize it, but I don't think it's asking us to. It's just saying, is A2 minimal? No. 1 and 1, 2 are equivalent states. Yeah, I mean, it's not asking, but I guess you could. 1 doesn't have looping C. No, but the idea is from, let's say we gave all these states numbers, or let's say we gave them letters like A, B, C, D. Okay, so C has 3 outgoing. We just care about the outgoing transitions. So, yeah, so C takes us to B. From B, C takes us to B. From C and B, both A and B will take us to D. So they have matching transitions, outgoing transitions, so we can merge those 2 into 1. But I mean, the question's not asked us to do that, so we don't have to. Okay, question 2. Oh, this is right. Consider this language here. A to the n, b to the m, a to the n greater than or equal to 0, m greater than or equal to 1. A language on over sigma equals AB. Prove that the language is not regular. Okay, so best way to start here is assume L is regular. If it's regular, then by Kleen's theorem, we can represent it as a DFA. Okay. So let's say we have our initial state. Let's try and make a DFA which accepts this language up here. If we read in a to the n, and then we read in b to the m, we have to read in a to the n to reach an accept state. So this is sort of what it would look like. But if we read in, say, n a's, and then we read in, I'm just trying to think of the best way to represent this actually.
So, proving that the language is not regular. So we have the language, oh my god. We have the language, a to the power of m, b to the power of m, a to the power of m. N is more than or equal to 0, n is more than 1, which is on the alphabet 8p. Prove that's not regular. So, obviously we've already done assume it's regular by cleaning this, it must have a DFA. And now we start to describe this DFA. So we will denote the state reached at an such that we have a to the power of n. So when we reach a to the power of n, right?
Yeah.
We get to state xn.
Okay.
And then we need to reach xm. Wait, hold up. Is it just that m is not equal to n? Because if it is...
I mean, no, m can be equal to n. It's just saying that we have a bunch of a's, then a bunch of b's, and a bunch of a's, where the a's are the same on the left and right of the b's.
Right. Okay. So that means that if we denote xn as a state reached after reading an,
Yeah.
then we have xn plus m, which is the state reached after reading bm.
xn plus m. Right, okay.
It's actually tricky, what the fuck?
Yeah, that's why I was a bit... Because there's two characters. Yeah.
Yeah, it's good though that we're doing this. So, when we have read x n plus m, I guess you could say that we must accept the same amount of a's as xn, but since we can't keep track, obviously we can't really check it, because obviously we're going from a to the power of n, b to the power of m, and then a to the power of n, where n and m can be any number, but n must be equal to n on both sides. So there must be the same amount of a's on one side and the same amount of a's on the other side. So I guess you could just generalize it down to the a to the power of n, b to the power of n, a to the power of n, really. Because that's a subset. We can just talk about L prime instead.
Is it a subset?
It will be a subset of a to the power of, I mean, a to the power of n, b to the power of n, and a to the power of n would be a subset of this, because it's just saying that we have everything where it's n, right?
Right.
Yeah. And so we can, instead of assuming L is regular, etc., we assume L prime is regular,
Okay.
where L prime is that, right?
Yeah.
And then what we can sort of start to do is prove that that is not regular instead. So we can say if we've reached a to the power of n at xn and a to the power of m at, actually we won't say m, let's say L, a to the power of L for another branch off the root.
Oh, right, okay.
Yeah. So basically I've just converted it into the same one. So
Right.
we have x to the power of L, and now if you remove that state in the middle, because you don't need it, you just need to get a to the power of, no, b to the power of n, a to the power of n, right?
Wouldn't this be a to the power of L? Or no?
Yeah, b to the power of L, a to the power of L. A to the power of L as well.
Oh, after this? Yeah.
Yeah. No, as in like, I mean, I guess that works, but you can do it all in one, really. yeah, a to the power of n, right?
Hmm.
And so this will only, so basically we're just saying that x of n will only accept b to the power of n a to the power of n, and xl will only accept b to the power of l a to the power of l,
Or we could
where
even
l
just
where l is not equal to n. Also, you've done it wrong. It's b to the power of l. Oh yeah, you can do that
but
as
then
well,
yeah, we can
actually,
say they're not equivalent.
yeah. So yeah, you've shown that here that they're not equivalent, and hence, because n is not equal to l, then they're going to be inequivalent for all of them. And so we can essentially not minimize this DFA any further, and because of that, we have an infinite or countably many states xn and xl, where xn is more than or equal to 0, and we can literally say like L is more than or equal. Actually, no, we can do L and M. I mean, L and N are both bigger than or equal to 1. Because we can't say that 1 is more than or equal to 0, and have
Yeah.
that work.
Yeah.
Yeah. So essentially, we've proven that this is now irregular because there's infinitely many states, and hence that contradicts the property of the DFA, right?
Yeah.
Because it's not finite.
Cool. Contradicts.
And
TF.
yeah. Yeah, I'll re-go for it. This is like actually my first attempt as well at this, so like that's probably why I've probably confused everyone. So my bad, I guess. But yeah, so essentially we've shown that that's not finite. So L prime isn't finite, hence L prime is not regular. So if we write L prime is not regular, since L prime is a subset of L, L should not be able to be represented by a DFA, because if we can represent L by a DFA, we can represent L prime by a DFA, and hence it must not be regular. Hence L must not be regular, because it contains non-regular a non-regular subset. But I'm gonna ask Todd actually.
Oh yeah, you're right. I did make a mistake on 1B. We accepted the reject state here. So which one would it be? I believe this one. B. Yeah, I think D should be a reject state. Yeah. Yeah, good spot. Cool.
So you could also talk about L prime, but I feel like a better way of doing it is if you have, because there's no bound on n and n, I mean n and m, right? So instead of saying L prime is n and n, we can actually, well, I think that's basically it. But instead of having n and n, it's just that m is equal to n at all of them, and hence the subset is same.
Right.
So it will just always be m.
Right. So we're just adding like another constraint to the end of this, basically.
Yeah. So where we have m is equal to n at all of them. But then, wait, hold up. That wouldn't make sense though, because if we had n is more than or equal to 0.
Yeah, so that would just mean n is more than or equal to 1 now. N can't be 0, basically. So
Yeah,
it's
but
still a
then
subset.
That's not representing the whole language though.
Yeah, but it's a
That's-
subset of the language, right?
Okay, I guess, but I don't know. I feel like there's a method to do it for like the whole language in one.
Yeah, maybe. I mean, does it really matter if this n is just an m like this? And we just do it for L like this? Because the idea is we still have two inequivalent states, and with the same input, one rejects and one accepts. So can we not just keep this as m? And then just say assume L is regular, and this whole thing's just on L.
I guess, but I don't know.
Yeah, I wish I had solutions to this one.
And it's the same. Yeah, because like I think Yusuf, the one that he put, is like quite similar, but they've done it for just all m.
Right.
But when n is equal to 0, then it's only Cm and oh, so if n is equal to 0, you just have a and b are non-existent, so it would be a branch from the root where we'd only have Cm.
C.
Yeah.
Where's C come from?
Oh yeah, I'm doing a different question.
Oh.
I'm just talking about. I'm just thinking.
Okay, let's look at this. 2023 summer paper, part C on question 3. Recall that primitive Java is a language with the type NAT and the following basic facilities. NAT equals 0. Okay, so these are the 5 things you can do in primitive Java. The following facilities are derivable from the above basic facilities and may be used in answering this question. Oh, this one wasn't too bad, to be fair. So to show the exponentiation function is primitive recursive, we just have to show that we can calculate this in Java. So we can just do something like, because I equals j to the k is just saying I equals j times j times j times dot 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 times j times j. And we're doing this k times, basically. So what we can do is we can say something like, we have our nat I is defined somehow, and we have our nat j is defined somehow. We don't have to define these, we assume that they're already defined. And for our encoding, we can just say something like, repeat k is also defined. Repeat k times, or what we'd do first is we'd say nat I equals 0, repeat, or no, nat I equals 0, and then if we do I plus plus, so at this point I is equal to 1, and so we can repeat k times I equals j, or I equals I times j, and this would just be the exponentiation function encoded in primitive Java, because what we're doing is we're saying k times, we want to times I by j, and so we're doing I times j times j times j k times by just encoding it with these lines. I think that was what was also in the mark scheme for that one. Yeah, so I equals 0, increment it, and then just times it by j k times. Yeah. But yeah, let's carry on with the 2022 paper. Okay, so we did question 2 with this regularity proof. Question 3, models of computation. Are these propositional formulas satisfiable? Ooh, we've got some maths and logic in here. Not complaining. Right. Okay. I don't expect we'd be asked something like this, but let's see if we did 2b. Is there a 2b? There is a 2b. Oh, okay. Give a context-free grammar that describes language L. Briefly explain your answer. Okay, so a context-free grammar that represents this language here. So we have our start variable. One sec. Okay, so yeah, we define a start variable, and we can take in, we know that n has to be greater than or equal to 0, so we could just have nothing, and we could just take in a b, because b has to be greater than or equal to 1. One sec, I think my OneNote's just bugged out. Okay, so yeah, it can be b because we have to have at least one b, because m is greater than or equal to 1. So it can either be b, or it can be a, and then something that's represented by the start symbol, and then a again. And to define, well, that's all we'd need to do, really, right? Here we have at least one b. What's wrong with this one, Ollie? How are you going to get oh yeah, we can have as many b's as we want, can't we? So this would actually be something like b s or a s. No. It wouldn't be bs. It would be, okay, let's make this s0, and then let's make another one called s, let's say this is just any number of b's. I'm going to make capital B any number of b's. So it can be B, or it can be B, B, or it can be epsilon. So this lets us expand as many b's as we want. Or we don't want the epsilon. Okay, so this is at least one b. And then we just want to wrap it. So we want to say A, S0, A. Right? Or AA, because we could have... No, we can't have 0 b's. Or just... Oh, no. ABA. Wait. ASA or B. ASA or B. Would that work? So we can have as many B's here, and then surround it with A's, and then surround that with A's. Yeah, okay, cool. Yeah, that makes sense. What's the thought process behind this? So, I mean, looking at... I don't know, it's kind of just intuition, I guess. So it starts with A's, and it ends with A's. So we're going to wrap something in A's. And then we could also just have B's with no A's, because n could be equal to 0. So we could just have b to the m, which is represented by this. This rule here lets us get any number of b's. So breaking it down into a bunch of different components, this lets us get any number of b's. And so our start symbol can either be any number of b's, or it can be two a's surrounding our start symbol, where our start symbol can be any number of b's, or two a's surrounding our start symbol, where our start symbol can be any number of b's, or two. So it kind of lets us build up our context-free grammar. Like it lets us derive any word that's in this language with this CFG. Should B also give S? So B or BS? No, because that would mean we can have A's in between. So the idea is B is just supposed to derive any number of B's like this. At least one B. So B represents B plus. And then S represents this language up here. Cool. Okay, question 3. Are these propositional formulas satisfiable? Yeah, I doubt we'd get asked this in TOC in 2024, but I mean we can try and think of a solution that satisfies these or doesn't satisfy these. If we use the sort of DPLL method, let's set a truth assignment to P. So let's say P equals true, and then let's backtrack. So P equals true, so that means we can get rid of this one. R equals true. Okay, so we can get rid of this. Not P or not R. Okay, so we got to backtrack. We got to now make S equal to true. We defo could get asked this. Oh, we could get asked. Okay, models. I guess. Have we covered this extensively in TOC though? Because I don't. I mean, yeah, it's good to be aware of it anyway. That's weird, but okay. S, let's say we set that to true, and we can cross that out. Okay, not P or not R. Okay, so R is going to have to be false. Okay, not Q or not S. Q is going to have to be false. Not P or not S. We can't have that, so we have to backtrack. I'm just curious as to whether they'd want us to do this, like whether they'd want us to run DPLL for a question like this, because it seems quite exhaustive. We did once like the second one, yeah. Because the only way we can really do this is brute force, really, or like an exponential time. Do they want us to do an exponential time algorithm on paper? Yeah, so for this one we have to start by setting P to false to cancel out this term. So, and then if P is false, then Q has to be true, in which case this would be false, or Q has to be false, in which case this would be false. So, this isn't satisfiable. For the first one it's not satisfiable. How have we worked that out? Or did we just sort of brute force every possible combination? Brute forced, right, okay. Because there's going to be PQRS, 2 to the power of 4, 2, 4, 8, 16 different combinations you'd have to go through if you wanted to brute force every combination, which seems like a lot of work for 6 marks. Okay, we've got a suggestion. If we say P equals false, Q equals true, R equals T true, and S equals false. So that's false or true. Okay, so that's satisfied. R or S, that's satisfied. Not P or not R, that's satisfied. Not Q, no. Not S, yes, that's satisfied. Not P, yeah. Okay, yeah, we found a satisfiable valuation for them. So this would in fact be satisfiable. Chris, did we just get that with like brute forcing different combinations, or did we use some systematic way of doing that? Pretty, okay, right. Brute force, I guess it is. If you get something like this, get ready to use up a page of zeros and ones. Okay, B. If P equals NP, then such satisfiability questions can be decided in polynomial time. Why is this? Someone just drop a sentence in the chat. Why can we do this? What? How do you answer this question? Okay, yeah, so there exists a ND non-deterministic polynomial verifier for the problem. Right. Any problem in P could be reduced to SAT. P could be reduced to SAT, so assuming we have something that can solve SAT, then we can solve P. Yeah, so anything in P reduces to SAT. Therefore, therefore, if SAT is in P, would imply that or actually, I mean, it's asking about satisfiability questions, so that is just SAT. But we're just trying to think how we could formulate a response to this. So, if P equals NP, then these satisfiability questions can be decided in polynomial time. Because we can convert polytime NDTMs into polytime deterministic Turing machines. And so anything we could previously do with a polytime NDTM, as per the definition of NP, we can now do with a polytime deterministic Turing machine. So we can then decide it in polynomial time. Draw the reduction graph. I don't think we will get asked for that. Let's cross that out. Yeah. Okay. Let's move on to question 4. Decidability and complexity following a spate of malware problems. Spate. I've never heard that before. A sudden flood, rush, or outpouring. Following a spate of malware problems. Oh, wait. So would a closed model answer be anything in P reduces to SAT? So SAT is in P, and it can be decided in NP and polytime. I wouldn't say it can be decided in NP and polytime. I'd say if SAT is in P, then we can decide SAT in polynomial time with a deterministic Turing machine. Because the idea is we're getting rid of those choose instructions, basically. Yeah, if it's in NP, it's decided. If it's in NP, it's verified in polytime. And if it's in P, it's decided in polytime. Okay, yeah, let's look at question 4. Following a spate of malware problems, several companies are reviewing their security procedures. The manager of Very Careful Limited instructs the IT team to write a program that can determine whether an app is able to corrupt data. Can this instruction be carried out? Explain your answer. The manager of Somewhat Careful instructs the IT team to write a program that can determine whether an app's code contains a signature of a known virus. Can this instruction be carried out? Okay, let's start with this first one. Whether an app is able to corrupt data or not is a semantic property. And is it trivial or is it non-trivial? Yeah, good. Semantic, right, and decidable. So this is semantic. Sometimes the app might corrupt data, sometimes it might not, so it's non-trivial. It doesn't always be true or always false. And so, as Ash said, by Rice's theorem, that implies that this is undecidable. Trivial is just, yeah, it's always true, it's always false. Non-trivial means there's some cases where it's true and there's some where it's false. This is a non-trivial property, because an app might corrupt data or it might not. Okay, and then you'd explain this in terms of the context. So can this instruction be carried out? No, it can't. They won't be able to determine whether the app's able to corrupt data or not because it's a semantic property. And by Rice's theorem, any semantic non-trivial property is undecidable. Okay, the manager of Somewhat Careful Inc. instructs the IT team to write a program to determine whether the app's code contains a signature. This is not a semantic property. And so we can do this. And so we just talk about an example of, oh yeah, Chris, for this, I'd probably say for non-trivial, just say some apps might corrupt data while others might not. That would be your example. You would just, you wouldn't say this app is secure because it doesn't have this line of code which deletes system32. You just generally say, okay, we can do this because we can do this. How can we do this? We can make an algorithm by reading each line and checking for the signature. So we can carry out this second one. For part 2, we just give the algorithm. Yeah, or you can just explain the steps of how the algorithm would work. Just show that there's a way we can do it. We can decide that. Okay. B, the following program takes as input a non-empty array P of A's and B's of length more than or equal to 0. Of length more than 0. Elapse 2 seconds, and then for every character except the last, we want to do this here. Wait a second. And then for every character, if pi equals b and pi plus 1 equals a, so if pi equals b and pi plus 1 equals a, then set this to b. So it basically just sets every character after the first b to a b. Okay. Give the best case, worst case, and average case running time for length n equals 3. So for n equals 3, we want to work out the best, worst, and average. Okay, so the best case, if n equals 3, is we could say they're all equal to b, because then we'll never actually go into this if statement. We could just say elapse 2 seconds, then elapse 1 second for every character. So 2 plus every character times 1 second, which is just 5. In the worst case, we go into this every single time. So if we have something like A or B, A. Here we'd do 2 plus 1 plus, so 2 plus, and then we do the 1 for every 3 of the input, plus, and we'd also go into here 2 times, because we'd say B and A, and then this would become a B, and then we'd say B and A, this would become a B. So plus 2 times 1, which is 7 seconds. Okay, and finally, on our average case, we want to consider every possible case. So we could have AAA, AAB, ABB, or ABA, ABB, BAA, BAB, BBA, BBB. I believe that's every possibility. And so, if it was AAA, let's see. We don't actually go into this loop at any point, so it's just 2 plus 3 times 1. If it's AAB, again, we don't go into the loop at any point, so it's just 2 plus 3 times 1. ABA, we go into the loop once. 2 plus 3 times 1 plus 1 times 1. 2 plus 3 times 1. Here we don't go into the loop, because after the B there's no A's. Here, we go into the loop 2 times. Plus 2 times 1. Here we do 2 plus... Do you guys see how I'm getting these numbers, by the way? Or is... So I'm counting the outer loop. We're going to do that for every character. And then the inner loop we're only going to do for every A we have to replace after the B. After the first B. Then we have 2 plus 3 times 1 plus... Here we'd only have to replace one character, so that would be 1. And here we have 2 plus 3 times 1. We're not replacing any of the A's because they're all B's. Okay, and then what we'd do is we'd add these up, and then we'd divide by 8. So, let's quickly do that. So, okay, so 2 plus 3 plus 2 plus 3 plus 2 plus 3 plus 1 plus 2 plus 3 plus 2 plus 3 plus 2 plus 3 plus 2 plus 1 plus 2 plus 3 plus 1 plus 2 plus 3. 45. Okay, so this should get us 45. Yeah, it's quite brute force, but what I'm guessing is with the n equals 3 and them telling us each entry is independent with A and B equally likely, I'm guessing they'd probably want us to write out all 8 combinations. So this gets us 45, and if we do 45 divided by 8, we get 5.625. 5.625 seconds, and this would be our average case time taken. So that's this first part. Okay, let's look at the second part. Show that the worst case running time is O of n. So in the worst case, we want to, it's n less than, so the first character being an A is the best, but it can only happen once. The best case is where they're all A's. It's n minus 1, so it only loops for n minus 1 times, right? Yeah, so it doesn't actually loop for that last character, because what we're doing is we're comparing the second to last character to the last character. If we looped up to the last character, we'd be comparing this character to a character that doesn't exist. It's like bubble sort, where we go up to the second to last element. Okay, so in the worst case, we're elapsing 2 seconds. And then, for every character, we're elapsing 1 second. And then, in the worst case, for every character, we're elapsing another... Ooh, no, this is wrong. Have I just done all of this very wrong? I have. Wait. Oh, okay, I've done this all very wrong. These, we're only going into the for loop twice, you're right, yeah. So it would be n minus 1 there. This would be 2 times this, 2 times this, 2 times this, 2 times this. Because we're only going up to, but not including n minus 1. So if n is 3, we're only going up to that. So we'd actually have 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 1 plus 2 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 plus 1 plus 2 plus 2 plus 1 plus 2 plus 2. 37 over 8, which is 4.62. That does not seem right. Why is the average better than the worst? I mean, why is the average better than the best? Same for the best. Oh, right, yeah, of course, this would be 2 as well. So this would be 4 seconds. This would be 2 as well. So this would actually be 6 seconds. And so we'd get 37 over 8 is 4.625. So this adds to 37. And 37 over 8 is 4.625 seconds. Cool. I hope that makes sense. Worst case, so in our worst case, we're doing 2 seconds at the beginning, no matter what the length of the input is. And then for every, so for n minus 1 of the characters, we're elapsing 1 second. So that's 1 times n minus 1. And then for those n minus 1 characters, if all of them are, so if it starts with a B and then the rest are all A's, this is our worst case because we have to replace every single character with a B, one by one. So this is going to be n minus 1 replacements, each of them taking 1 second. So this is going to be plus another 1 times n minus 1. So this gets us 2 plus 2n minus 2, which is just 2n. Show that the worst case running time is in O of n. So now it's just a matter of proving that 2 of n, or 2n, is in O of n. And what do we need to do that? How can we prove that? What do we need to find? Yeah, okay, we need to find our m and c values. So there exists some m and there exists some c such that for all values of n greater than or equal to m, 2n is less than or equal to c of n. Boom. And this shouldn't be too hard. We can just say c equals 2 and m equals, I don't know, we can say 0. We could put any number here, really. That's positive. And this inequality here holds for this. And so, therefore, 2n is in O of n, and so our worst case complexity is still linear. At which point did I lose you? So in our worst case, we're waiting 2 seconds, so we have that plus 2. Just the last column. Oh, okay. This part here. Okay, so we're saying we want to prove that 2n is in O of n. So the question was asking us to prove that this is the worst case running time is O of n. So to do that, we just need to show that there exists some value of m, so a lower bound, or we could say graphically, our m is this intersection point, or anything greater than or equal to our intersection point. And we want to find the c, which is the multiplier of that function, such that for all n greater than or equal to this cutoff point, our function, so f of n, is less than or equal to c times g of n, where g of n is what's in the O of n, so g of n is just n, and our f of n is just 2n. So this is just mathematical proof for bigger notation, and we're just showing that we found that constant 2 and that m equals 0. And so 2n, or the worst case complexity, is still linear in O of n. Awesome. Okay, we'll start by looking at this question then. I think someone wanted to take a look at this. Question 4 on complexity. In the popular puzzle Sudoku. Oh yeah, just for reference, this is from the 2016 paper, question 4a and 4b. Okay, in the popular puzzle Sudoku, a square grid of n squared by n squared small squares are displayed, divided into the n by n square subgrids, each consisting of n by n small squares, and partially filled with numbers in the range 1 to n squared inclusive. The task is to fill all the remaining squares with numbers in the range 1 to n squared inclusive, in such a way that in each column, each row, and each subgrid, every number appears precisely once. Here's an example with n equals 3. So we want to fill this with numbers so that in a row, all of the numbers are unique. In every column, all of the numbers are unique. And in every subgrid, all of the numbers are unique. So just standard Sudoku. Okay, so this is an example of a partially filled grid. And this is an example of a solution. So how we could fill in that grid to have a fully filled in grid. Not every partially filled grid is solvable. Explain why solvability of a partially filled grid is in NP. Okay, so the idea is we have these partially filled grids, and we can not exactly solve this in polynomial time. We cannot deduce a valid grid in polynomial time that we know of with any algorithm we know of. But what we can do is we can verify it in polynomial time. So we can verify a solution in polynomial time. Can anyone talk me through how we might do this? Oh, sure. Hello.
Hello.
Hi.
Hi. So this question is asking why is the solvability in NP? So if the solvability is in NP, it means that there exists a polytime checking machine that can tell us if a solution, if a given solution is valid. And basically what we need to do is we need to show that there is a polytime checking machine. Or like design one, not necessarily like draw one out. So what you could say is that when you have a given solution, there's going to be n. Is it n? I think it's n squared. N squared like as a length and n squared as the width. Yeah.
Yeah.
So there's going to be a maximum of like n squared times n squared with like n to the 4 pieces or cells to check. It's
Okay.
in reality going to be less than this because some of them are obviously already filled in.
Right.
But there in this case, if you'd want to go through, you'd go through each and every single row. Firstly, I'd go row first. You'd go through each and every single row and check that each number only appears once.
Good. Yeah.
And therefore going through each row would take n squared steps because you go through each number and you check that the rest of the row doesn't contain that number, aka only appears once in the row.
Yeah.
So that takes n squared steps, and you do that for all of the rows. So there are n squared number of rows.
Yeah.
So it actually becomes like n to the 4.
Yeah. Good.
And then same thing for the columns. Takes n squared to check that the number exists once in a column, and then n squared to, like, there are n squared columns. Therefore, that's also in n to the 4. Therefore, the final complexity of a deterministic checking machine to validate a solution given would be in O of n to the 4, which is polytime.
Okay. So it's in polytime, but yeah, we also need to.
No, we need to do the subgrids. Yeah,
Yeah.
subgrids.
So
So the subgrids, you just add it on. So you know how this summation you're doing on the right, yeah. So you just add it on. But the thing with the subgrids is they'd actually be lower complexity. So you'd end up with n. N. Would it be n? There's. Okay, so each subgrid is of size n. Therefore, it would be n squared still to like check, wouldn't it be?
I mean,
Because you'd have to look at the grid, look at each and every number, and also go through the list again for every number to check that it's not there twice.
Yeah, so it would be the same for this, and the same for this, and the same for each subgrid as well. But one thing to note is, so we're just considering looking at all the cells, but then for every cell, we also have to look at every other cell in that row. So it's actually O of n to the 6 for all of these. Just because if we think about it, if we're trying to see if something exists, we have to look at every other element to see if it's equal to that. So we're looking at every possible pair of elements. So first we're comparing 5 to all of them, then we're comparing 3 to all of them.
Well, you're not comparing 3 to all of them. You're comparing 3 to just the ones in the same row or the same column.
Yeah, so for example, we have to compare this to n squared minus 1 different values, and then we have to compare this to n squared minus 1 different values.
So it's not just n squared because what you're saying is that you're comparing all the squares in a subgrid to every other subgrid, where we're actually doing all the squares with every subgrid square. So if I do it like that, then it would be n to the power 4 because the space complexity is n squared times n squared, and because we're comparing each of them to n squared of the subgrid, it then becomes O to the n6. But then I would do it differently just because it's a better visualization. So what I would do is, if you look at the rows technically, right? So if you look at that first row on the left, like the long one.
5, 6, 1. Wait, no, 5, 3, 4. Yeah.
So if you look at that, that's n squared, right?
Yeah.
That's n squared in that.
Yeah. And then if you look at the other 3, that's n cubed, right?
The other 3?
So like 5, 3, 4, like, and then all the way down, that's n cubed, right?
5, 3, 4.
How do I like draw on your computer?
Wait, so do you mean like the entire 5, 3, 4 and going all the way down to the bottom?
Yeah, 5, 3, 4,
Or like just those 3 columns, Shay?
Yeah, so that's n cubed, and then that's 3. 3 squared is 9, which is all the subgrids, which is then n cubed squared, which is n to the power 6. That's how I would do it.
Okay.
Yeah.
I mean, regardless, it's still in polytime.
Yeah.
Yeah, like if your time complexity is wrong, we're gonna mark you down on that because they're just like that. Because I basically did the same thing in like one of the summatives, right? And I said it was in polytime, but then they said that although your method is in polytime, you did the time complexity wrong. So I only got like 2 marks out of 4.
Wait, so if you give like any checking machine in polytime, surely it's correct because you've still shown it's in NP. It doesn't matter what the polytime.
No, but if you've calculated the time complexity wrong, you lose marks for that, even if it's in polynomial.
Right. So
Yeah.
in Sudoku, hang on. So does every single number of the subgrid also need to be unique, or is that irrelevant?
What do you mean every single number of
So
the
as in
subgrid?
like, you know, the 3x3 grid,
Yeah.
does that also have to have all unique values? Oh, okay, right. So
Yeah.
we need to compare every single value. So that's just another n squared, though, isn't it? Because you're comparing each value to like n squared minus 1 other values.
No,
Regardless.
because we have n squared in a subgrid, right?
Yeah.
So like the n times n grid, the small one.
Yeah.
Yeah. Let's say we're comparing it to one other subgrid. So because we're comparing 2 n squared grids.
Why do you want
that
to
would
compare it
make-
to another subgrid, though?
to check that they both. Oh wait, hold on.
We just care
You
about
never
looking at all of the rows,
Yeah.
all of the columns, and all of the 3x3 grids.
Individual subgrid. You
Yeah,
never
yeah.
compare it to another subgrid unless it's like in the same column or the same row.
Yeah, you're right. I'm just waffling on.
Okay, but yeah, so this is the like calculation you'd do. This is the mark scheme. So there's n squared times n squared minus 1 distinct pairs of entries because you have to compare everything with everything else in the same row or in the same column. And yeah, comparing with subgrids is the exact same complexity as that because we're just comparing with n
because
squared minus 1.
we're just comparing. There's nine values in the subgrid, so that's n squared, and you're just comparing each of those with 8 other values, which are the other values in the subgrid.
Yeah.
So it's just going to be n squared because that's the number of values, and each of those has another n squared to compare with.
Yeah.
So it's going to be n to the 4.
Yeah, and then we times that by n squared because we're checking for
Because
uniqueness.
there's n squared number of subgrids.
Yeah, Ilya, no diagonal. We just care about columns, rows, and subgrids. Cool. Okay, let's look at part B. It has been shown that this problem is an NP complete. Explain what that means. What does it mean for a problem to be an NP complete? Or what does it mean for this problem to be an NP complete?
What, me?
Anyone? Okay, so this problem is both in NP and in NP hard. Yeah, thanks for that, Adwit. Both in NP and NP hard. What does that mean in the context of this problem? Or what does that mean? Because the mark scheme was trying to get a specific definition. I'm guessing we'd still get marks for this, but it just feels like for 7 marks, this might not be... I feel like getting 7 marks for this and getting 7 marks for this is definitely not not equal. But yeah, the problem is both in NP and NP hard. What the mark scheme suggested, and I think Ash has also said that, is every problem in NP can be reduced to it in polytime. So any problem we have that's in NP, we can reduce to an NP complete problem in polytime because it's at least as difficult as every other problem in NP. Yeah. Cool. Does that question make sense to everyone? NP hard, yeah. So NP hard is NP hard is a subset of NP, and NP complete is... Oh no, NP hard is not a subset of NP. That is wrong. NP complete is a subset of NP hard, and NP hard is just as hard as hardest problems in NP. NP hard is not a subset of NP. It's the hardest. It's the same difficulty as the hardest problems in NP, but it's not necessarily in NP. So if we have NP and we have NP hard, then NP complete would be this part here. NP complete, yeah. Complete is, yeah, because it's both in NP and it's as hard as the hardest problems in NP. Exercise 1. The following program uses recursion to compute a binary function b on natural numbers. Okay, so it's not quite the Ackermann function, but it's another, looks like it's primitive recursive. Show that it terminates for all m and n. Okay, so assume, or let's say, let me type this out actually. Let's say q of m n be true if b terminates for, or b m n terminates. I don't want to write spaces throughout. Okay, q m n is true if b and m terminates, and false if b m n does not terminate. Okay, so let's start with our outer inductive. So we want to show that q of m n implies q of m plus 1 n. Okay. Or actually, we want to use course of values here. Okay, let's just go ahead with this. Okay, so we want to show that QMN implies Q of n plus 1n. So we know that Q of B of, or let's look at our base case inductive step. We're told we want to use course of values, so let's change this to our basis. In our basis, what are we going to have? What's going to be our basis for this? M equals 0. Okay, so yeah, we've got two things. M equals 0. Why is it capitalizing? M equals 0, n equals 1, and then we have m equals 1, n equals 0. Oh, right, no. Okay, there. M equals 0, n equals 0, and m equals 1, n equals 0. Are we sure that would... How I'd go about doing it is probably saying n equals n, like this. Okay. So let's say we had something like this, and then we know that this terminates... Oh, right, yeah. Okay, so we'd use that as... Because they all terminate. Yeah, okay, so those are base cases in the algorithm. For our basis for m, though, I'd probably say, let's say, if m is 0, then q of 0n will terminate as b of 0n equals n plus 7, and q of 1n will terminate as b of 1n equals n plus 5. Okay, so this is our basis. We've managed to do that. Okay. Inductive step. Now we're going to use an inner induction here. We're going to say show that q of m n... Wait, let me think about this. Okay, so we've proven that. We want to show that q of m n... Ooh, okay. This is actually going to be for all n. So that qmn implies qm n plus 1. Oh no, this would be for all m actually. Okay, so to show this, we'd have another basis, and we'd say this basis would be n equals 0, because this is one of our base cases for n. And when n is equal to 0, q of q of 0, then q Q of, sorry, M, and then when n is 0, for all m, because that's the thing we're sort of changing in this induction. So we're showing that Q of m n implies Q of m plus 1 n. We're not really worrying about the n here, but the m is, we're showing that for all m we terminate. And in here we're going to show that for all n we terminate. So basis n equals 0, Q, so here we're going to take in m, and as our n we're going to take in 0. We're also, I think we should also have 1 as a base case, because that is also another, yeah, m0. Okay, so if we take in Q m0, this will terminate as b m0, b m0 equals m plus 17, and Q m0, m1, sorry, will terminate as b m1 equals m plus b m plus 1 9, and b m plus 1 9 will terminate given the outer inductive hypothesis. Does that look right? Okay. Inductive step. So our inner inductive step is we want to show that this holds. B m plus 2 1 equals. B m plus 2 1 equals. Oh, right. So this would actually be b m plus 2 equals. So this would be m minus 1 essentially. So this would be m minus 2 plus b m minus 1, and b m minus 1 will terminate. Right, because since m minus 1 is less than m. So this is our outer inductive hypothesis being used. And then for our inductive step here, we'd say, okay, let's think about this. So we're so close. Q of m one thing we could do is we could say Q of mn implies Q of m plus 2 n plus 2. So we could say that we can prove this by saying if we pass in b m plus 2 n plus 2 equals, or this can even be for all values less than it doesn't have to be that. B m plus 2 n plus 2 equals b m n plus 7 plus b, or this will be n plus 5, and this will be m minus 2, plus b m n. And so n minus 2. No, just n. Minus 2. Okay. B m minus 2 n plus 5 would, or this is true, will terminate given the outer inductive hypothesis, and m n minus 2 will terminate given the inner inductive hypothesis. So Q m plus 2 n plus 2 will terminate as a result. I believe that would be that would be what we reach, and then therefore Q m n holds for all m and n. Why b? Okay, so the reason I did that was because b m plus 2 n plus 2. This is the same as writing b m n maps to b m minus 2 n minus 2 plus 7 plus b m minus 2 plus 2 n minus 2. All I've done is I've subtracted 2 from all of the occurrences of m and n. And so this would now be b m minus 2 n plus 5 plus b m n minus 2. So that's why I got that. I wrote n plus 2 on the left. Yeah. Oh, you're right. So this would actually just remain as m n plus 7 m plus 2 n. I feel like right. Then we'd have to use. Okay, so that would change some of these steps. That would say q of m plus 2 n plus 7. No, sorry. Q of m n plus 7 will terminate given the outer inductive hypothesis, because the outer inductive hypothesis states that it holds for m less than m plus 2. And then m plus 2 n will terminate given the inner inductive hypothesis, because n is less than n plus 2. So this will terminate as a result. I believe that's what we'd do. Let's compare that to this, right? So to treat m equals 0 and to treat m equals 1, we just show that it terminates, which we did down here. Okay. If it's m to m plus 2, I believe. Right, okay, so they did m plus 2 here, and then they said that just maps downwards. So I guess this would have to be m plus 2, but everything else doesn't really change there. We prove that for all n in natural numbers, it halts by course of values induction on n now. So first we did it on m, now we're doing it on n. To treat n equals 0, it halts. N equals 1, it halts by the outer inductive hypothesis. Yep, because m minus 2, or m minus 1 is less than m by course of values. Okay, and then to treat the case n equals n plus 2, we obtain that it halts for m plus 2, n plus 2, because this halts by the outer inductive hypothesis, and then this halts, by the inner inductive hypothesis, and so the whole thing halts because it returns two constants which are a result of it returning a value, and so it all terminates. We should probably use the term terminates and not halts. But yeah, cool. Yeah, so we have our outer induction, we have our inner induction, and then we reach that conclusion.